In this video we're going to explore the consequences for XPS spectra that are measured from samples that have been prepared in different ways with the identical material. The sample that we're measuring by XPS is an aluminium foil that has an oxide layer, then a metallic aluminium, and the underside is also an oxide layer. And the difference between how these samples are being prepared is whether or not this sample is electrically connected to the sample holder, and whether the bottom or the top of the sample is electrically connected, or in the third case where the sample is isolated from the sample holder, and this is the situation where charge compensation will be required to maintain a steady potential for this sample. The first observation one would make looking at these three different spectra measured from three different samples is that all three have a similar shape, that is to say an aluminium oxide peak that is relatively broad and then a relatively narrow metallic peak, and all three can be seen to have these characteristics. The difference that is then most obvious is that the isolating sample has been shifted to a higher kinetic energy. So this implies that the sample has been raised to a negative potential, and therefore electrons are accelerated away from the sample and hence produce a higher kinetic energy. The first two spectra were measured without charge compensation, and in this case we can see by eye at least that the metallic peaks seem to align. However, we need to use the peak model that has been defined on these data to see that there has been a difference in the position for these oxide peaks. The annotation table, as displayed here, is showing the offset between the peak that is the aluminium 2p3/2 metallic peak, and then the next one is the aluminium 2p3/2 oxide peak. We can see here that the offset between these two peaks is 2.33. However, when we look at the second spectrum, and this is the one that is grounded on the top, then the same offset is 2.07. So there is a difference here as a result of measuring these two samples that should be identical using a different sample preparation. And then if we look at the example where charge compensation has been used, then the offset between the metal and the oxide of the aluminium 2p3/2 is now 2.44. So all three measurements are reporting a difference in binding energy for these aluminium oxide peaks, but the sample is identical, and the difference between these measurements is how the sample was prepared and whether we used charge compensation or not. As a general rule, when we observe spectra such as these, it's a good idea to repeat the measurements, and so the experiment that was performed on these samples was repeated 3 times. So these spectra represent the first measurement for each of the grounded at the bottom, grounded at the top, and isolated, and these are the tables that we saw previously. Now we can change the display by selecting the VAMAS blocks corresponding to the grounded sample from the bottom, and I will display these in the active tile. We can see this in a bit more detail if we zoom in, and I'm going to make use of the region that is defined on these peak models to zoom in, and then we can see, if we turn off the display of the annotation, that the metallic peaks are very much in the same position regardless of the measurement of the sample that is grounded on the bottom. However, using the cursor and pointing at the position of the 3/2 peak, you can see that there's a movement of about 0.2 from the first measurement to the second one, and then with respect to the third measurement, from the third to the first, there's about 0.5. So what is happening when we have a sample that is grounded is that the oxide appears to be moving away from the metal peak the longer we measure these data. So this would suggest that the aluminium oxide is being charged positively with time, and that would be consistent with an insulator that is not being charge compensated, and therefore a positive charge builds up and the peak is then moved to lower kinetic energy on the basis that the positive charge is attracting the electrons that are being emitted back towards the sample, hence the lower energy. Now we can equally look at the grounded at the top and see that a similar pattern is emerging, that we have a movement of the oxide peak while the metal peak remains constant. So the metal is maintaining the potential, but the insulating oxide is charging positively. Whereas if we look at the insulating sample that is charge compensated, then there's an offset in the energy, but the relative position of these peaks between the metal and the oxide is very consistent. So the charge compensation for the isolated sample is maintaining a constant potential between the oxide and the metal. A comparison of these data has been made easy by virtue of this peak model and various markers that are display options within CasaXPS. So what I'll do now is go through the various display features that have allowed these data to appear in the format that we see here. The appearance of this peak model depends on a parameter that has been specified within the quantification parameters dialog window, the components property page, and that is the component index. Each component is assigned a different index number in this instance, and this has determined the colors that are used to display these data. And this is because, in addition, there are options that have been enabled on the colors property page that say color components using component index. And then there's combine component index. So this means that if we have two components with the same component index, then the intensity for the two components will be summed to form a display of the combined components. And then we have fill combined components, and hence we see the fill color for each component rather than just the outline of the component. There is one further tick box that is enabled for this display, and that is mark component position. And because this is enabled, we have these vertical lines that are indicating the position for each of these components within the peak model. So I used this so that I could give a visual feedback of whether these oxide and metal peaks were aligning or not. The color used for each component is determined from a palette of colors that can be modified using the synthetic components button to produce a color property page, which then allows the modification of these colors. So for example, I could adjust this color here, make this slightly darker, and then press the add to custom colors, and it updates this value here. So these are the colors that are used by the component index, in the sense that each one of these is assigned a component index. This is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when we have two components, as in this case, that are assigned values of 2 and 10, the outline for each one of these components is determined precisely from these colors. The fill color is then a color that is derived from these outline colors, and so we end up with a set of components that are colored according to the component index and the values for the colors that we see in this palette here. I'll close this, and I will close this window so that we can then bring up the component property page with the values that are currently specified. So if I move this over, we can see here we've got a set of component indices which can be modified to change these colors based on what we saw in that custom palette. So for example, I might set 10 to 2 and press return, in which case both of these two components are coloured using the value that we see here of 2. And then the envelope for both of these components is the sum of the two components, and they are both filled using the same colour. So now we can see the advantage of these markers indicating the position of the actual components. So we can see here we have a peak that is drawn as a single component, but it actually consists of two components where the centres are marked here with these individual markers. In this example there are only 4 components, but in other peak models there may be multiple components representing sets of doublet peaks. So there are options in terms of keywords that allow us to adjust the component indices en masse. And in order to return all of the component indices to their default value of -1, there's a keyword reset. So when I enter this keyword and press return, the component index is set to -1 everywhere. We can also use a keyword that says set equals and then specify a value. So I've entered set equals and let's say 3. And what this will do is any component with the same component index, and these are all -1, will be assigned a new value of 3. So now we have all components with identical component index, and so we see a single envelope with a single fill color for all the components when they've all been summed. And then, because we're dealing with doublet peaks, there is another key string, group equals 2, and this is designed to allow sets of doublet peaks that are arranged sequentially within the components property page to be assigned appropriate component indices. So because I've specified 2, what this means is that the component index will be left at the current value for 2 components. So this first one and the second one will remain at a value of 3, and then it'll be incremented for the next 2. So when I press return, the doublet nature of these peaks is reinstated, where I've got 3, 3, 4, 4, so we get 2 different colours. And the idea is that you can build relationships between peaks in terms of colours. That's one form for the display, but it's also useful if you want to update, for example, the line shape. So if I were to set this value to be 843 instead of 943, and then use a character hash, when I press return with this hash character in place, it will then update components with the same component index. So the line shape is updated in the first 2 to have the same value as the value I entered in A, but because we have a different component index here, these line shapes, which are different because they're metallic line shapes, these have been left alone. If they all had the same component index, then all the line shapes would have been updated. So this is a way of separating components for building line shapes or transferring information such as RSFs or names that we would like to assign to components. These are all updated on the basis of whether the component indices match or not. So it's not just colours that the component indices work for. Now if I wanted to change these colours, I could make this, say, 2 and make this one 5. So we can see that the component indices are also making a difference to the order in which these peaks are plotted. If I change this one to say 2 and then make this one 3, you can see that the first one plotted is the component with the lower component index. There's one more keyword that can be used with the component index, and that is the keyword step, and it will apply to all components with identical component indices. So the first thing I'll do here to illustrate it is to reset all of these component indices to -1. So they all now have the same component index. If I enter in the first column, though it doesn't necessarily have to be the first column, the word step, then what this does is it enters 0 for the first column, 1, 2, 3. So we've incremented the component index along these columns within the component's property page. And what this means is that the component colors, as indicated by these component indices, will be the same as the default colors that would be used to plot components.